Hi guys, so we'll start with some applications of differentiation and especially of stationary points, which we've just been doing. Optimisation is simply the process of finding the best possible solution for a given situation. So often with these questions we'll often be asked to find the maximum or the minimum value of a function in order to use our differential calculus knowledge. So we'll be asked to find the maximum or the minimum using differential calculus. Now when we're doing this we can follow a set of steps. Really important in these to draw a well-labelled diagram, because that is going to help you heaps with actually being able to picture what the situation is. Then you want to construct a formula for the variable being optimized. So say it's asking you about the maximum cost or the maximum area. You want to have a formula for area with the area as the subject of your formula. So for example, if you think of the formula y equals x squared plus 3, if you're talking about area you'd want it to be a equals x squared plus 3. You want to express the formula as a function in terms of a single variable. What that means is, for example, if we're thinking of a rectangle and we're doing the area of a rectangle, that would be length times width. The problem with that is that you've got two variables that makes it hard to work with. So you want to find some relationship between width and length in order to be able to express it as one variable. We want to discuss the logical domain. So what that means is, some things, a radius being less than 0 just doesn't make sense. You can't have it. So you only want to work with the numbers for your x, or for the variable that's being taking the place of x. You only want to work with those numbers that are actually in real life relevant. So we'll do all of that and then we'll finally differentiate. Once we've got that formula in terms of one variable, we'll differentiate. We'll equate it to 0 and then solve. So this is the same process pretty much as what you've been doing with stationary points. You've been equating to 0, solving for x. And then you've been drawing a sign diagram to determine any maximum or minimum. Alright? And you'll recall how we talked about local maximum and minimum because of the fact that your endpoints might be a maximum and midpoint and minimum. You probably should check them to see if they are. Then we identify the optimal solution, so the one that's the smallest or the biggest depending on which one we're asking, and we write a sentence of conclusion that actually answers the question. No point just randomly putting stuff down if you don't refer back to the question. So you need to be sure to answer the question actually asked. Okay, so we've got this question. We've got a loop of string of length 100 centimeters. So I'm just going to write down some of the information as I read through this question. So I've got my length of string. That's telling me the perimeter is 100 centimeters. I want to find the area, the maximum area that can be formed using this loop of string. I also know that it's a rectangle, so I can draw in my rectangle. I know that the area of a rectangle, if I call this x and this y, I don't know what x and y are, but I know to find the area I'm going to do x times y. So I know that I want to have area as my formula that I want to maximize. It's in two variables, so I somehow need to work out a way of writing it in only one variable. Now I'm going to use that bit of information. I've been told that the perimeter is 100 centimeters. We've got two sides, so that are of length x and two sides of length y. So 2 lots of x plus 2 lots of y is going to equal 100 centimeters because the perimeter is 100 centimeters. Now this is great because this means we can just write y in terms of x. We get y equals 100 take 2x, and therefore 2y equals 100 take 2x, therefore y equals 50 take x. Now let's go and write our area formula. So now area equals xy. Now we're going to replace the y, remember, by 50 take x, and we'll just expand that to make it simpler, 50x take x squared. So we've now got our formula in terms of one variable. The next step was to differentiate that. If we differentiate the area, we're going to get 50 take 2x The next step after that was to find when the derivative is equal to 0. So a dash of x equals 0 when 50 take 2x equals 0. And that is going to be when negative 2x equals negative 50, and therefore when x equals 25. Now the final step was to find the sign diagram. So remember, we often find the sign diagram of the derivative, not the actual function, because we're interested in the slope and if this is a maximum or a minimum. So we're just going to do the sign diagram. One thing that I forgot to do, which I should have done earlier, was to work out the logical domain. That was a step up there. So our logical domain, obviously x has to be greater than 0 and y has to be greater than 0. So 50 take x has to be greater than 0. So negative x has to be greater than negative 50, and so x has to be less than 50, because when you put that into, when you divide by a negative, you switch the inequality sign. So that tells us that 0 has to be less than x, which is less than 50. Right, that's our logical domain. So let's put our endpoints on here. 0 down here, 25 here, and it can't be bigger than 50. We can then check our slope. So I'm going to pick something in here, and when I pick that in here, I'm just going to pick a number. So I'm going to pick 30. Find a dash of 30. That is going to be 50 take 2 times 30, which is negative 10. So that's less than 0. It's going to be negative. Now we talked about this the other day. You know that a dash of x is 50x take x squared, so that's a quadratic. That tells you that it's going to have a turning point. It can't have a stationary point of inflection, so it's going to change sign over 25, which means it's positive or going up that side, and then negative slope coming down that side. So that does tell you it is a local maximum, and you can check the dimensions of the endpoints if you want to, but if you put 0 into your equation, you're going to get 50. So you'd put it into this equation and you'd get area of x would equal 50 times 50 take 50 squared, which would tell you that it's a negative number. That would come out as a negative number, so that doesn't make sense. And if you said it was 0, your whole area would be 0, because you're substituting into the equation a of x equals 50x take x squared, which obviously when you substitute in 0 is going to give you 0. So neither of those are relevant in this situation. You don't really even need to show them, though you can. And so obviously then the maximum area is realized when x equals 25 centimeters. And that would be your answer. You would actually write it like that. Alrighty, so the next one's a little bit more complex. You've got a simple cylindrical can, so let's draw a diagram. It has a volume of 500 centimeters cubed. So find the dimensions of the can, so that's saying the radius and the height, which would minimize in this case. So not maximize, it would minimize. That's the radius and that's the height there. Remember when you're doing a cylinder that to find if we unravel the can and put the middle there and the top there and the bottom, the top and the bottom, the length of this side along here is actually the same as the circumference of that circle. If you unravel that circle, you would get the length along there. Alright, so we know therefore that the length of that is 2 pi r. We know that the height is that. Okay, now you want to find the dimensions of can, which minimize the area of the metal sheet. But before you do that, you want to use your volume information somehow. So you've got volume equals 500 centimeters cubed. Remember, you want to be able to write your area formula in terms of only one variable. Alright, and we know that the volume formula is pi r squared h. So we can use that piece of information to actually be able to do that. So pi r squared h is going to equal 500. And then if we find h is therefore just going to equal 500 over pi r squared. Now that's great because when we use our area formula, we now have height in terms of the radius. So the area of this cylindrical sheet, the area of this metal sheet from which my whole cylinder is cut out of, can be found using the formula for area of a cylinder, where you've got the top and the bottom of the cylinder. So the top and the bottom of the cylinder are circles. Formula for area of a circle is pi r squared, so that's going to be 2 pi r squared. And then to find the area of that rectangle in the middle right here, it's going to be length times width, so that's going to be plus 2 pi r times the height in this case. Alright, if we substitute in those values, we will get that the area in terms of r is, and now I'm going to write it all in terms of r, so I'm going to get rid of my h, 2 pi r squared plus 2 pi r times by height, and height is 500 over pi r squared. Alright, now I can cancel some things here. Be careful with your cancelling that you don't do anything illegal, and I get 2 pi r squared plus 100 r to the negative 1. Now notice I actually haven't done any differentiation yet. Alright, now you should all be yelling and screaming because I haven't done one thing again. I didn't do my logical domain. Remember, my logical domain has to be, so this makes sense. How is this going to make sense? Well, the radius has to be greater than 0, doesn't it? The height has to also be greater than 0 because they're dimensions. But we also know that the height can be written as 500 over r squared, so that's got to be greater than 0. And that will be as long as, that will be greater than 0 as long as r is greater than 0. So that is true for all r greater than 0. Alright? So therefore r has to be greater than 0, which we already knew. Now, so now we've done that, we're just going to differentiate our function. We're going to find a dash of r. So a dash of r, let's multiply down, subtract 1. It's going to equal 4 pi r. Take 1,000, this should be 1,000 in here, can't multiply, 1,000 r to the negative 2. And we can now write that, and it's probably easier if we write that now as fractions. So 4 pi r, take 1,000 on r squared, because r to the negative 2 is r squared. Now if I want to write that as one fraction, I'm just going to multiply the top by r squared, because if I do that, that means I can put it all over r squared. Alright? Because what I've done to get to this step, remember, all I've done is I've multiplied the top and the bottom of that by r squared. Alright? Now a dash of r equals 0 when that top line equals 0. When 4 pi r cubed, of course the bottom can't equal 0, so we're just interested about the top, equals 0. So therefore 4 pi r cubed is going to equal 1,000, and r cubed will equal 1,000 divided by 4 pi. To be able then to find r, we're just going to have to cube root that. Alright, so as r is going to equal the cube root of 1,000 divided by 4 pi. Yep. And if you put that in your calculator, you get 4.30 centimetres, 3 significant figures. Alright, now let's do a sign diagram of that. Next step, sign diagram. Follow those steps, you'll be fine. It's like following the yellow brick road. So if we do the sign diagram of a dash of r, what we get is something that looks like this. Well, we know that r is to be greater than 0. We don't have any limit on it. We know that r is 0 at this point. Not r is 0, the derivative 0 is at that point. So let's just try a point bigger than that. Let's find a dash of 10. If you put that into your calculator, that is going to give you a number that's greater than 0, so that's going to be positive. Again, we just have to probably check the other side this time. We have to do that because we know that our derivative is actually a cubic, so it could be a stationary point of inflection, so it's worthwhile checking the other side. If you check the other side, pick a number less than 4. So say we did a dash of 4, I'm not going to work that out for you, you would get a negative number. So that tells you that yes, truly it is a local minimum. Now, when r actually equals 0, when r equals 0, you would get, again, you would get actually that the area is equal to 0. Because remember, when r is equal to 0, let's look at this. This would be 2 pi by 0 plus 2 pi by 0 times h. Okay, so that would equal 0. So that's definitely not going to be a minimum, as you want to minimize it, but you do actually want it to exist. Alright, so we've done that, we've done the sign diagram, but we still haven't answered the question because we want to find the dimensions of the can. So this is where it's really important that you actually answer the question. We've worked out that there's a global minimum. There is a global minimum when r is 4.3, because r has to be greater than 0, so it can't be equal to 0. When r equals 4.3, then h equals 500 over 4 pi over pi times 4.3 squared, which is actually equal to 8.60 centimeters if we're doing it to 3 centimeters. 3 significant figures. Remember, if you're doing to 3 significant figures, you need to pop that 0 on the end. And so therefore you'd answer the question. The can, so dimensions are, the radius would be 4.3 centimeters and the height equals 8.6 centimeters in order to minimize the area. And that is how you optimize. It's a long question, but it's not that hard if you follow the steps. Okay, hope that helps. Bye.